Hello everybody, this is Danny from the University of Campinas. Today I am going to talk about how we can use the idea of ANI, Abstracted Network Inventory, for a streamlined service placement in distributed clouds. This is a joint work with Christian Rothenberg, Mateus Santos, and Pedro Gomes. Scenarios for distributed cloud with multiple edge clouds and centralized data centers are being investigated as computing and networking foundation of next generation of network services. For example, virtual reality, augmented reality, self-driving vehicles, smart cities, drones, etc. So, what is a distributed cloud? A distributed cloud is a cloud execution environment for virtual or physical network functions or applications that is distributed across multiple cloud sites, such as edge sites, regional sites, or central sites, with the required connectivity between them. Distributed cloud deployment models keep latency-sensitive applications closer to the edge of the network, that is, close to the users, and move not real-time application to centralized data centers. For example, this figure shows interconnected edge sites in which a centralized orchestrator or central orchestrator can establish communication with local orchestrators placed at individual edge sites. Examples of open source projects that consider multiple edge cloud sites and centralized data centers include Akraino and ONA. An Akraino deployment, for instance, intends to follow the hierarchy of deployments, such as the collection of central sites that deploy a collection of regional sites, and the regional sites facilitate the deployment of edge sites. In such distributed cloud environments, multiple cloud sites can become candidate hosting targets for network functions in a network service, so that, given a set of service requirements or components or demands, placement decisions are necessary to find the best cloud site for each of the components, where a new service instance can be placed. For example, resource demands in terms of CPU capacity and performance demands in terms of bandwidth. Or, for example, CPU capacity and bandwidth constraints along with anti-affinity rules. In order to take optimized placement decisions, orchestrators, central orchestrator or local orchestrator, need to maintain an inventory of the network, providing a real-time representation of the available resources in the network infrastructure and their relationships. For example, compute and storage information or information of the connection between virtual machines or hosts. However, a typical service provider will have hundreds or thousands of edge and regional cloud deployments, including tens of central cloud deployments. The size of a network inventory may become very large in distributed cloud scenarios. Therefore, management systems, central orchestrators or local orchestrators, face scalability challenges when processing large amounts of data to decide where to instantiate a service or part of the service. A common system engineering principle to deal with scalability requirements is to introduce proper abstraction mechanisms. Some examples of resource abstraction mechanisms are one big switch abstractions, graph-based abstraction, or cluster-based abstractions. Each of them has pros and cons regarding the topology information view, accuracy, security, computation complexity, etc. The novel abstraction method presented in this paper is directed to the abstracted network inventory component, ANI component, that, in addition to receiving the network inventory as a first input, ANI also uses service requirement as a second input to generate service-optimized network inventory views called logical network inventory, LNI. Using a logical network inventory delivers two main advantages. First, a reduced time for placement of network functions because resource candidates for the placement are logically reduced in terms of the number of compute nodes and links in comparison to the original representation in the network inventory. And second, a summarized topology per service can be used to simplify and optimize the management of resources. An example of management is the lifecycle operations, in which service resources should be rearranged, such as the scaling network function of workload. Now, I am going to be more concrete regarding the ANI component, key concepts, the generation of a logical network inventory, and so on. We need to consider two basic definitions, network inventory and a network service. Network infrastructure resources are represented in the form of a network inventory. A network inventory may comprise node and edge, each providing a particular capacity. Examples of node-related capacity are the number of CPU, the amount of RAM, the amount of disk space, etc. Examples of the link-related capacity include bandwidth characteristics and latency characteristics. A network service is deployed or instantiated over the network infrastructure. A service specifies one or more nodes, that is, a set of required network functions, and edge, how network functions are connected. Nodes include resource demands, for example, CPU, memory, storage, and edge contain performance objectives, for example, latency and bandwidth. A two-step procedure is performed to generate a logical network inventory, LNI. In the first step, a classification of a service is performed to determine whether the service is node-oriented, edge-oriented, or not an edge-oriented. In the second step, the actual node and/or edge-oriented mode is executed over the network inventory to generate a logical network inventory, LNI. The first step, service classification, may be executed, for instance, calculating the resource and performance reference values in the network service. In the case of the resource reference value, it can be computed as the sum of CPU demands, and in the case of the performance reference value, it can be computed as the maximum bandwidth objective. On the other hand, for the network inventory, we can determine a node reference value as the sum of CPU capacities as well, and the edge reference value at the average or worst-case link capacities in terms of bandwidth, for instance. Then we compare those values to determine if node and/or edge are relevant for the placement. For example, if the performance and resource reference value are greater than the node and edge reference value, it means that the node and edge capacity in the network inventory are under-provisioned. Therefore, node and edge are relevant for the placement, and the service is classified as node and edge oriented. On the other hand, if only the resource reference value is greater than the node reference value, it means that the node capacities in the network inventory are under-provisioned. Therefore, the service is classified as node-oriented. Otherwise, the service is classified as edge-oriented. Other different mechanisms may be used to classify a service. It will depend on whether we want, for instance, to minimize the amount of resources consumed, if we want to minimize the bottlenecks, among others. However, such mechanisms are out of the scope of this work. Once the classification of a network service has been done, the process of building up a logical network inventory is in accordance with such classification, so that we have three different types of logical network inventories. In a node-oriented LNI, a set of nodes in the network inventory are assigned to the logical network inventory. Edge are discarded. Such selected nodes have to support the CPU capacity constraint of network function nodes in a network service. In an edge-oriented LNI, a set of edge in the network inventory are assigned to the logical network inventory. Selected edge have to support the required bandwidth capacity of edge in a network service. Finally, in a not edge-oriented LNI, a set of nodes and edge in the network inventory are assigned to the LNI. Node and edge are selected according to the CPU and bandwidth capacity constraint in a network service, respectively. Now, I will present the formulation of the ANI network model along with the introduction of the algorithm for the generation of the three different LNIs. So, we model a network service as a directed graph denoted by G sub S, where B sub S is a set of network functions connected via a set of directed edge E sub S. Each network function B sub S is associated with a requested CPU capacity value CPU B sub S. And each edge E sub S connecting two network functions Y and Z is associated with a requested bandwidth capacity value BW E sub S. In our network model, we are considering a basic scenario with only CPU and bandwidth constraints. additional capacity constraint of nodes and edge can be easily extended in our model. On the other hand, in its basic form, a network inventory is modeled as an undirected graph G, where a node B sub I has an available CPU capacity CPU B sub I, and an edge E sub I between two nodes N and M is associated with a bandwidth capacity BW E sub I. We also denote the set of all loop-free paths from a source S to the destination node D by P sub I. And the available bandwidth capacity of a path member of P sub I is given by the minimum bandwidth value in all the edges that are members of the path P sub I. In order to support graph collections, our network inventory model is extended to include a set of logical network inventory graphs, where LNI sub I represents multiple possible views of the same network inventory. We model an LNI graph as an undirected graph as well, where LNI nodes are a subset of the original network inventory nodes, and an LNI edge are a subset of the original network inventory nodes. Eventually, LNI graph may be overlapped. Given a service request and a network inventory, our objective is to determine a logical network inventory graph optimized for a service requirements in terms of nodes and edge constraints. Here we illustrate the LNI generation with an example. On the left side, we have two network services where the numbers in rectangles represent the requested CPU capacity and the numbers near of the line represent required bandwidth capacity. The network service 1, NS1, connects to network functions, network function 1 and network function 2, with 45 units of bandwidth on the edge between them. The network service 2, NS2, requires the bandwidth 5 over the edge, NF2 and NF4, and 15 units over the edge, NF3 and NF5, and different CPU nodes requirements. On the right side, we have a network inventory. The number near of the links is the available bandwidth, and the numbers in the rectangles represent the available CPU resource and the node. Once the process of determining an LNI is performed, the network inventory contains two logical network inventories, L sub NS1 and L sub NS2, where each graph has a dedicated subset of nodes and edge, which represent an optimized network view to the requirement on each network service. Note that the node C is overlapped for both logical network inventories. As I mentioned, the LNI component considers three modes of LNI generation. Therefore, we propose three different algorithms to efficiently create an LNI. In this algorithm, we have the pseudocode of the node-oriented LNI mode. It takes the network service and a network inventory as inputs and returns a set of nodes. So, for each service node, the algorithm searches all nodes in the network inventory and adds nodes with CPU capacity greater than or equal to the CPU requirement into the subset of nodes in the logical network inventory. This another algorithm provides an overview of the edge-oriented LNI mode. It also takes a network service and a network inventory as input. However, besides the set of nodes, it also returns a set of edges. So, for each service edge, it first iterates all the possible network inventory nodes to get a source node and a destination node. After, the algorithm finds the path from such source node to the destination node and only considers those paths that respect the bandwidth requirement in a service edge. Finally, all the nodes and edge which are in the path will be part of the subset of nodes and edge in the logical network inventory. The node edge-oriented LNI algorithm is quite similar to the previous one, except that in addition to the bandwidth requirements, the CPU constraint of the service node should also be satisfied by the CPU capacity of the network inventory node. Finally, we analyze the performance of our proposed algorithms. For that, two evaluation environments were considered. First, the quality of the LNI using randomly generated network inventory topology, and second, the LNI impact on the network service provisioning time using a real graph dataset. It's important to highlight that all the supporting codes are publicly available in our research group repository. For the LNI quality evaluation, different network inventory topologies were randomly created. The number of nodes varies between 20 and 100. The CPU and bandwidth capacity of a number distributed between 1 and 16 and 1 and 100 respectively. And the LNIs are created from service requests with a number of network functions between 2 and 6. We use two measures of nodes and error reduction and the degree to evaluate the quality of LNIs generated by the three different algorithms. This figure shows the normalized reduction of nodes and edge with different network topology sites. As we can see, the node reduction by the node-oriented LNI algorithm achieved the higher values, and its edge reduction is 100%. This is because node-oriented LNI algorithm only considers nodes supporting the CPU constraint, and edge are discarded. Besides, edge-oriented LNI algorithm achieves the lowest node reduction value because it traverses all the nodes without restrictions. On the other hand, the edge reduction measured by the node edge-oriented LNI algorithm is higher than edge-oriented LNI algorithm. This behavior is expected because the node edge-oriented LNI algorithm only considers node and edge supporting the CPU and bandwidth constraint respectively. We also computed the relationship between compute nodes and edge, that is the density in an LNI with different topology sites. The degree measure is always 0 for the node-oriented LNI because edge are no longer considered and therefore all the nodes are isolated. In general, LNIs are densely connected. However, edge and not edge-oriented algorithms always achieve much lower degree values than the baseline, that is the density in the full network inventory. We also set network services with different amounts of network function from 2 to 6 on a network inventory topology with 100 nodes. As shown in the figure on the right, the value of the degree is decreasing as the number of network function increases. This is because a new network function adds new CPU and bandwidth constraints. Therefore, we can infer that the number of network function decreases the number of node or edge supporting such requirements. We also quantify the time it takes for an orchestrator to map a requested network service considering a logical network inventory. We use a real network topology obtained from the Internet Topology subproject. Specifically, we extend the Internet route topology to represent a full network inventory. This topology contains 110 nodes connected through 148 edge. CPU and bandwidth capacity were the same values of the previous experiments. For the central orchestrator, we use the escape tool that supports several parts of the service chaining architecture, and it can run on a number of emulated local orchestrators. Escape also includes a simple service layer where user can request network services. In this experiment, we measured the escape's time-saved rate for mapping a service. This value is defined as a fraction of the amount of saved time using an LNI topology and of the running time using a full network inventory topology. Results show significant improvement in terms of saved time when the orchestrator uses an LNI compared to the approach in which a full topology is used. More specifically, the key observation is that a central orchestrator can achieve up to 50% time saving for service deployment with the reduction of less than 20% of nodes in a network inventory. Or even with a reduction of nodes and edge by less than 55%, it's possible to obtain up to 75% time saving rate. It's important to indicate that this preliminary evaluation doesn't consider the time needed to generate an LNI. It's only considered the time needed for the placement once an LNI is already generated. Okay, just to quickly summarize, one of the challenges for management systems in distributed cloud environments is how to effectively handle the scale and complexity of network service placement and management, considering actual resource network inventories. This paper contributes with a novel component called abstracted network inventory that generates optimized network views called LNIs, based on the network service requirements and network inventory capability. Our results show that when using a logical network inventory methodology, we can reduce the time to place network services while optimizing the management of resources by following the principle of abstraction, that is, by the logically reduction of set of candidate resources in terms of computed nodes and links. As next steps, we will extend the three proposed offline algorithms, which typically comes at the expense of long ramp times, to online algorithms implemented via heuristics. Also, we extend our network model to consider other decision variables such as cost or revenue. And regarding the experimental evaluation, we will consider more complex network services and more complex infrastructure resources. And we will analyze the total time of generating an LNI and placing the network services. Okay, I'm done. I would like to thank you for your attention, and I will be happy to take any questions.